Okay, so today we have a talk by Mikko Kurimo, who is professor of speech processing, and he's going to talk about speaking assessment systems. So please go ahead.
Okay, thanks. And yes, thanks for inviting me here. And also for people in Kumpula, if you have any questions, you can just unmute yourself and ask. I can't follow the chat here, so it's better that you just raise up your talk and ask. Yeah, so this is the work that we have done in the project, academic project called Digitala, involving 3 partners. So my team at Aalto, so Rakel, Katja, Jaroslav, Clara, and myself, and then the team in University of Helsinki, Anna and Riley, who are actually working in the teacher education part, so the language didactics, so no computer science knowledge. And then Jyväskylä, there's also in the education people there who are responsible for these UKI tests. So if you apply for Finnish citizenship, you have to go there and take a test of your Finnish skills. So these are the people who are guarding that. So Ari, Heini, and Mikko. And my title is very long. I'll go through it slowly. So it's an automatic speaking assessment system for spontaneous second language learners' speech. So basically taking the speech test where you describe some image or tell about your summer vacations or something like that. And in under-resourced languages. So it's not in English, so it is for other languages where the resources are very limited. And in our case, Finnish and Swedish. And then the machine learning related title here is towards transparent and explainable AI. So basically we want to be able to show that why our system is giving certain results and what should the student do to improve his skills. And here are some of the research questions. Maybe these explain even more to you what we are trying to do. So we want to know how to do automatic speaking assessment using automatic speech recognition, so without using human. And then do this self-supervised learning and pre-trained models that are very common in ASR nowadays. Can they actually solve the ASR problem in spontaneous speech in under-resourced languages? So basically in the cases where we don't have enough target data. And then which features are important for computing an automatic speaking assessment, ASA? And what about using explainable features or black box system? How much we suffer. And then we want to know which of these features are most effective human speaking assessment. So we have human reference assessments, but maybe those experts don't even know themselves that what are the actual features that they are paying more attention to. So we also want to analyze their assessments and show them that, okay, this was the part that we paid most attention. For example, in Finnish, is it like the correct pauses or the duration of the phonemes that is often difficult for non-native speakers. And then how can we make a classifier to get the overall proficiency level from these features? And can we predict the overall level from the assessments in these analytic dimensions of speaking skills? Or is it better to do from scratch, or basically from the data itself? And then do this speech-to-text errors, do they matter for this speaking assessment? So certainly our ASR system is not going to be perfect, so do these errors matter? How much? And then finally, how to compute feedback for the students using these various aspects of speaking skills. For example, to say, look, your pronunciation is not that good, maybe practice that, or maybe the use of language, you make too many grammatical mistakes, maybe take attention to that. Then we give this kind of feedback. The project started a couple of years ago, or 3 years ago actually. So we have finally managed to get some publications out of it where you can read more. There are master's thesis of Jaroslav and Clara, and then we have a paper in the main conferences, speech area, the interspeech. First, last year we had a paper about this ASR system, and then this year we had a paper. Well, it was not accepted to interspeech, but it was accepted to something that is even better. This IEEE workshop on spoken language technology. Just last Friday it was accepted there. And then we have a journal article which is still on review, as we were for about a year already, where we give more details. And unfortunately that is anonymous, so I can't give them content to you yet. And then we have a video. I wonder if I could show the video here. What would happen? At least the people locally here might be able to follow it. So this is a kind of 3-minute short summary of results. Oh, Helsinki is hosting the meeting. Can you see this in Kumpula?
Speaking of our language can be manipulated task.
No, we cannot see it.
Where to practice so at your own pace and time, while at the same time receiving the personalized feedback. We in the digital projects have decided that
This is Rahe, one of our students.
to practice and assess speaking so for Finnish and Finland Swedish. While this is not a physical task, Dr. Kurimo from Aalto University will talk more about that.
So, essentially, our goal is to develop a tool like this using the up-to-date internet technology and the data part speech and language technology. So the task of automatic speech recognition is to convert speech to text and separate the words from RN words. And based on this, we are analyzing the speaking skills in 5 different dimensions. So, task completion, fluency, pronunciation, range, and accuracy.
So to get the speech sample from human language, we've designed a prototype tool to collect speaking samples from language learners with different proficiency levels. Dr. Riley Alden from the University of Helsinki will tell us what this means in practice.
We have used an online module environment for collecting data from language learners and human raters. We have designed automatically accessible speaking tasks that fit to a certain proficiency level, following both the Finnish curriculum and the CEFR. CEFR is the common European framework for reference, an international standard for describing language ability on 6 levels. In addition to analyzing speech samples and human ratings, we have also explored stakeholder beliefs, that is, the teachers, human raters, and language learners' perceptions on automated speaking assessment. Their feedback and opinions help us to improve the system faster.
Dr. Haley Cowell from the University of Lexico will explain further.
So before we teach the machine to assess speech automatically, we want to know what's going on in speech that makes some language learners gain higher grades by human raters than others. And for this, we at the University of Lexico have made comprehensive acoustic analysis that uncovers the features that are characteristic for each proficiency level. We can, for example, measure the relative amount of pauses and hesitations in speech and try to find some thresholds that separate speakers with regard to their fluency level.
So this is a great opportunity to combine research and technology to develop this online tool that will enable students to practice their language skills reliably and cost effectively, and this can come in a situation like national meetings, examinations, and other high school steps. Very versatile environment.
Okay, so if you lost this video in Kumpula, you can Google for it, or I can send you the link so you can watch it later. Okay, so first about this under-resourced problem. So Both this speaking assessment, automatic speaking assessment, and self-learning with automatic speech recognition, they are rapidly growing fields at the moment. The second language learner speech, as you can imagine, is very hard for the speech recognition system because even the speakers don't know the language perfectly. So they will have all kinds of very strong accents and they make a lot of disfluencies in their speech, a lot of hesitations and disruptions, and then the pronunciation can be whatever it is. Also the kind of language structure can be very weird. But we still want to kind of exactly find out what they are speaking so that we can rate it. And yeah, so this is very, well, there are many low resource tasks here because collecting big databases of non-native speakers or language learner speech is very hard. So typically all the big speech databases are from native speakers, or at least very skillful non-native speakers. But if you ask any non-native speaker, can you provide us data, then typically they don't, but they are not so happy on that because they feel that they are not very good in that language, so they don't want to speak, at least, or donate it for public use. So this is very scarce data resource. And this is even more challenging for low resource languages like Finnish and Finland Swedish. Even if you find some data in non-native English, you don't find it for these smaller languages. But then special challenges for the automatic speaking assessment is that there is a lack of human reference assessments. So basically all the samples will need to be assessed by at least one human expert. And these are much harder tasks than just transcription of the language. So basically they need to think that what is the level of the speaking. So typically we need to pay a lot, and then it takes time, and the group of possible experts is much smaller. So we are never going to get enough of those human reference assessments. And even if they are great as such, they are typically, the data is very unbalanced on different levels. So we might get a lot of, let's say, A2 or B1 or B2 speakers, but those who are close to perfect, it might be difficult to get how to find those speakers, or those who are absolute beginners may be difficult. So we are kind of missing data from both ends. And finally, if we ask several of those human experts, they typically don't agree. So they might give different grades. So that is, of course, a challenge for automatic systems of how to take this into account. Human references are not perfect. And then the final challenge is that what can we give as kind of understandable and useful feedback for language students? What would make their language learning better? If we just say that, okay, according to our data, that your speed of talking is not fast enough, but it doesn't help if they start speaking faster, and it doesn't make their speech more understandable. But that is a typical feature that is correlated very well with the speaking skills, that how fast you can speak. But we can't tell that directly, so we need to tell something else, what to practice. Okay, this is the system that was also quickly passed in the video. So basically the idea here is that these are the different dimensions of speaking skills. And here we show that kind of everything here is based on the speech signal, and this automatic speech recognition engine affects somehow in all of these. So if the speech recognition fails, then everything else basically fails here as well. So it's very dependent on that. Most, of course, in this language-dependent feature, like is the correct question answered, or is the range of the vocabulary and language. So these are very dependent on speech recognition, but also the kind of pronunciation and fluency. We need to find out that where are the phonemes and how they are pronounced. So this kind of alignment is based on the speech recognition. So, solution for first talking about the speech recognition problem. So this is a picture of a conventional ASR system, where typically you have speech going in and then words coming out. Then you extract some features and then also decoder. And the decoder not only listens to the speech, but it also takes into account some acoustic model, which has been trained with a lot of data, some kind of lexicon, what words there are, how they are pronounced, and then finally some language model saying that this is the Finnish language, what are the words and how they are put together. The problem with the traditional system is that we need this kind of customized engineering for finding the pronunciation dictionary and language model. And these are particularly problematic for language learners, since they are not probably using the standard pronunciation dictionary. They have their own pronunciations, maybe affected by their native language. And also the structure of the language can be different. So if we kind of force everything to the standard Finnish language, then it might hide some of the mistakes of the students or then go completely to the wrong track. So this modern version of the end-to-end ASR, we basically bypass all of these separate models and go directly from input speech to output words. So this is in a way easier solution, but the problem is that this one requires large amount of transcribed speech, which obviously we can't access. So then what comes to help of us is these self-supervised acoustic models, which can be first pre-trained using a big untranscribed out-of-domain speech, and then just fine-tuned for ASR using a small transcribed target set. So here we could imagine that we could take any speech data in Finnish and train this big model on transcribed self-supervised model using the transcribed data. Just the kind of model to get some idea that what is Finnish speech and then extract some features of it. And then we could use these features to train a classifier to do the speech recognition. So this could help us out of this training data problem. So what kind of results we got here? So what we showed already in our third paper is that we can quite convincingly outperform the traditional ASR system because the data is so small. So if we use the small data to train a system, then it is much worse. So for example, in the Swedish, we got something like 12% instead of 17%. And we use the pre-trained model, and Finnish about 22 versus 38, whatever percentage. So really dramatically better than the conventional system. So here we use this big self-supervised model trained on other data in individual Swedish. Of course, then when we talk about this pre-trained model, so the common architecture is made to get tool, which is nowadays used for many things. The data is typically trained with 5,000 or even 50,000 hours of speech. So obviously there are no way to get two models for every language in the world. So what we did, so there was luckily a model for Swedish, for Finnish there is. So we compared what is the accuracy of the monolingual versus multilingual model. And we see that it really is better if we can have a monolingual model. So it would make sense for us to train a large pre-trained Finnish model, because in Sweden we got better results compared to the multilingual ones. One other observation is that we can measure the performance in many different ways. So word error rate is just the kind of how many words are correctly or incorrectly recognized. But we could also measure the character error rates. So even if one character is wrong, then the whole word is wrong. But if just one character is wrong, then maybe the word looks quite okay. Even the native readers won't necessarily notice all the errors there. So we can measure the character error rate. There the improvement compared to this traditional ASR is even more remarkable. So we can get less than half of the errors there. So maybe that is even in our application, it's even more important, this character error rate, because it now can tell us that what did the person actually try to speak. So even if we make kind of partially correct words, we can still reflect those with this error measure. So unlike the traditional systems with language models and lexicons, this kind of end-to-end models, they actually decode also the non-standard words outside of the training data set quite well. So they are not favoring the kind of official words. Obviously, we can still use language model here and get improved word error rate, but we didn't because we were not sure that is it something that we want. Probably we actually want to get these non-standard words out so that we understand what the student is speaking. So we didn't want to use the language models here. So this system actually also decodes the speaker, his fluency or his pronunciation, which is what we want. But basically here in the ASR side, our contributions, so we were able to develop completely end-to-end second language learner speech recognition without using any external language model or pronunciation dictionary, which means that we can produce it for any language if we just get a pre-trained model and some target data. And then we demonstrated that the self-supervised pre-trained model can adapt to low resource L2 using only a small amount of fine-tuning data. Of course, people have shown this before for kind of, let's say, in-domain tasks. So if you have English pre-trained model, you can adapt it to certain speech recognition tasks with very small amount of data. Facebook has shown it, and also others. But what we here show that we can actually kind of be able to adapt it also for out-of-domain data. Like we have this language learners data, which is not exactly the same as the native speaker's language, and it works here as well. And yeah, so we can also show, we have shown that this pre-trained data doesn't have to be second language learners. It can also be native speakers or even speakers from other languages in the multilingual data. Okay, then we did the speech recognition, and now we go to the speaker speech assessment experiments. So the data here, so this is just a portion of the speech recognition training data. So we have even less data, but those data that have been rated by human experts. So we cover something about like 200 Swedish speakers and 300 Finnish learners. There's not that many hours, so basically there are like short samples from all of the speakers. Only about 6 hours in Swedish and 14 in Finnish. Rated by human experts in 7-level CEFR the scale, so A1 to C2, and actually the 7th level is something below A1. But we didn't have any samples really on that, maybe 1 or 2 more. And for this data, okay, maybe I can tell you, maybe I should tell here that since this data is quite small, so we did speech recognition of assessment experiments using this kind of like 5-fold cross-validation. So basically we divided the data into 5 parts and then just used 1 part for testing and 4 for testing or training, and then we switched this 1 part. So, and with this work we got error rates here 17 for Swedish and 16 for Finnish. So Finnish improved quite much because we had a lot more Finnish data here in this experiment than Swedish. Maybe this is the good picture to tell something more about the data. So here we have the levels of skill levels starting from A1 to, okay, we didn't have any C2 speakers, and this vertical axis is the amount of samples for each level. So we see the most speakers were A2 or B1. So it's really quite unbalanced data. And here we have the word and character error rate for separately for each of these levels. So what we see here is something that is very understandable, of course, that the better the speaker, the easier it is to recognize his speech. The closer it becomes to the perfect speaker, the lower the error rate. Yeah, so this looks very clear for Swedish. And for Finnish, there was something different. So first of all, we got some speakers also. It's better in the C2 area and also a bit less imbalance there on the levels. What we see also is a big difference here in word error rate and character error rate, which is very explainable because Finnish words are longer. And so typically if you make one small mistake, it makes the whole word incorrect. So that explains the difference between the red and yellow word. The basic shape is the same, so basically decreasing. Then of course we don't have hardly any samples here, so you can't really trust the beginning of the curve. And also at the end of the curve, the amount of samples is smaller. But what we see here is an interesting kind of increase of error rates when the speaker becomes very good, which we didn't have in Sweden because we didn't have very good speakers. What we hypothesized here is that once the speaker is very confident and close to native, they start using more difficult words, like loan words from English or other kind of rare words. And that is, of course, harder for the speech recognition system as well, because they are less in the training data. So that might explain it. But of course, that is not very large difference. So we are still around 20 word error rate or 7 character error rate, which is pretty good. Okay, then we wanted to see what features affect the overall rate. So we used two different kinds of features. So one feature was this, what we call P&L features, where P is for pronunciation and for fluency and L for lexical. So basically we had some experts to think about different measures of these dimensions and then computed a lot of features on both. So for example, speaking rate was one, or articulation rate, or acoustic model score to tell about the pronunciation and so on. And then the other set of features, so we used this Lexico-grammatical pre-trained model and actually used just some bottleneck features out of there. So basically took the middle layer there. This seemed to be a good idea, but in some cases also some other layers might be more useful, or somehow using even several layers might be good. So these Lexico-grammatical features were first pre-trained with unsupervised L1 speech, and then it was fine-tuned for ASR, and then finally we also fine-tuned for the speaking assessment level, so basically modify the weights to get better results in there as well. And the results here, so here are the different feature sets, and here we have two criteria here to measure. So we first measure the precision and recall there, and the F1 measure. So basically we wanted to do this because it a bit more balances between the different levels, since we have quite imbalanced data. The bigger is the F1 score, the better, and also the Spearman correlation measures about the same thing, although with correlation statistics, so the bigger the better. So got quite okay results with these manually selected on the PFL features, but it seems that the way-to-back kind of black box features are even better. And then when we combine the two, again the error rate or the performance improves, which basically tells us that they are kind of complementary features. But these kind of automatic features find out something that the human-made features didn't. And then if we train this later features for the assessment results, we got even better results. Okay, that's again Swedish data behaved nice. Finnish data we didn't have that, didn't get that exactly the same performance. So we saw that the later two features were better clearly than the TFL, and also actually the Spearman correlations in Finnish were quite high. And then we saw that this combining the features or fine-tuning again didn't have that much in Finnish. So basically the errors are quite insignificant after the breaking in the black box features. So these are the results that were just accepted last week. And here we analyze that which of these manually selected features actually affect most to the overall grade. So we selected like 10 best of the features. Something for pronunciation, something for fluency, something for lexical features. So no surprises here. Some features are quite easy to interpret, like the length of the response in words or the speed of speaking. But some are more difficult, like this pairwise vocal indexing. I don't even remember what it meant. Something that is more difficult for the students to understand. Okay, so then we are thinking about this feedback question. How do we tell to the students? So we took these 5 aspects of human assessment: task completion, pronunciation, fluency, range, accuracy, and then saw what they are actually. So this explains how these are basically explained for the human experts. What are these? I guess they kind of make sense, so there is no surprises here. Maybe this one anecdote, this task achievement that we first didn't pay much attention to. We thought that that's easy to check. But it turns out that even the human experts seem to disagree quite much, basically. We thought that it's like on off. Are they cheating or are they answering the correct question? But apparently there are a lot of gray area between it. And humans are not always agree on those. Okay, so how do we compute feedback on these 5 dimensions? So basically we train 5 evaluators to do this. So we had this overall evaluation already earlier, but now we train for these 5 different aspects, also different evaluators. So for that we had the human assessment for each of these, for all the samples. And then then we have to use some automatic features, something that it would be possible to compute automatically. So for example, this task achievement, we computed the semantic distance of the attempt towards the correct answer, which if we have the correct answers, it would be possible to do, but if we don't have the correct answers, or if we wanted to do in a way that it's not dependent on the task, so if we didn't have a different evaluator for each task, then we just needed to do basically the prompt, which obviously is a bit problematic. Even though we filtered out the distance of prompt or other invalid answers. Okay, then the results. So here we have different systems. And here again we use the F1 measure, Spearman correlation for Finnish, and here it was Swedish. And here we wanted to kind of be as transparent as possible, so we didn't use any black box approaches. So basically we had these explainable features, and then we just trained the register 3 classifier. When we compare this resistant tree classifier to the kind of completely black box model, that we saw that at least for Finnish we was quite much. In the performance for Swedish we didn't. Yeah, so of course there is some problems with the human assessments and also with our data, so we don't have all the kind of fine-grained levels for each of these 5 factors. So for example, in pronunciation, there was actually significant data only for 2 levels, basically good pronunciation and okay pronunciation. No sometimes really bad pronunciation. So kind of the number of levels varied in here. And here, interestingly, since this is kind of only transparent, we can also kind of turn this into a regression path and then actually compute the formula of this, how to get the final grade with these kind of sub-grades. So you can, this A is for accuracy, so we see that the factor here would be 0.3 and then 0.01 for 6 for pronunciation, 71 for range, and 49 for fluency, and 27 for task completion. So this is not normalized to 1, but at least it shows us directly that for Finnish the range is quite important here. The pronunciation is really not that much affected, at least in our data. And if we compare to Swedish, which is again not normalized, we see that the level of the pronunciation is much more important in Swedish. The range is much less important for these human graders. And also the fluency is less important here. And the final set of results that I could show today is when we kind of focused mostly on the lexicon and grammar features of external computing from the speech-to-text output. And this is the work of Clara, her master's thesis that accepted last month in August. So we used the same data, so the German coefficient, she used also the mean square error, so basically showing that whether you are making mistake to the next level or previous level, or basically doing a big mistake, making errors of many levels. So there, of course, the smaller number is the better. So first, she studied the kind of effect of ASR errors here, and doing everything twice, like first with human transcripts and then with ASR transcripts, she showed that there is actually no significant difference in there. So less than 10% error. So basically showing that these automatic results are, or automatic transcripts are valid for this. So basically what is the good interpretation is that the error that the speech recognition makes are in kind of areas that are less important for rating. So often they make errors in kind of not in the content words, but in some less meaningful words, like something that is not pronounced very clearly in even native speech. So this was good news. Then she also compared whether this affects more the accuracy or range, and kind of supporting my hypothesis, this affects more on the accuracy part, so kind of the grammatical accuracy than the range that is more about the rare words. Then we use these PFL features, so the handcrafted features, and compare it to BERT. So basically we can use the BERT model to kind of find all the features about the language and train the model on that. But really the handcrafted features are pretty selective, they are quite comparable. So there's no big differences. Typically the BERT features are a little bit better, but no big differences here in either range or accuracy. And then with their research, we tried whether this more advanced Roberta model would be better than standard curve, but again, it was only slightly better. So, no big differences. And then finally, she compared whether this kind of random forest model, which is a bit more explainable model than standard TNN, whether it would give good results, and this is the RF here against the DNN. And basically, what was seen here is that they are quite comparable. So we don't need to use the black box model here, we can just use the more explainable classifier. Okay, so for the conclusions, so speech recognition seems to work reasonably well for this task, despite the lack of training data. The explainable features seem to work okay, but black box features usually better. And also the explainable classifiers work okay, but sometimes the black box classifiers will work better. So if you're just interested in the classification results, then this kind of fully neural approach is better, but if you want to kind of have some explanations, then the other one is more useful, or you can do both. We saw that this kind of analytical dimensions, they provide more detailed feedback from the student, although it's harder to explain their effective overall grade. So typically, if we want just to estimate the overall grade, we don't need to care about this analytical dimensions, but it's only for the feedback they are useful. And the biggest challenges here were the unbalanced number of samples in the classes, and also the inter-annotator disagreement with human references. Yes, and here you can find the links for the project video that I showed you, and then we have a short demo or basically explaining this Moodle interface that students can use for this, and then other results in general. And for the rest, you just need to ask me. Okay, I think that concludes my presentation. I guess we have some time for questions still.
Yes, thanks a lot for the speech. So, any questions here or from Kumpula?
Maybe one question. What kind of error rates are we currently getting in the well-sourced languages? And what kind of error rates would we need for practical usage?
Yeah, so if we talk about Finnish language, because error rate means a little bit different thing in other languages. So in Finnish, we get something like 20% for spontaneous speech, and then therefore some kind of more grammatical or kind of planned speech, like the parliament speeches, we get less than 10% error rate there. So we are quite close to this native speech already, because this kind of domain of speaking here is much simpler. So typically, because the speakers are not so skilled, they choose, when they speak spontaneously, they choose like easy constructs and easy words. So in that sense, we are, the material is not that bad as we might think first.
But with this error rate of 8% already allow for fully automated training, or would that still be too high to really transfer the feedback?
Yeah, I think as I had in the last slide, that kind of our biggest challenges are elsewhere. So in these human experts, they are maybe the biggest challenge, and also getting data from all the classes. Of course, speech recognition makes some errors, but they seem to be smaller than the big challenges.
Maybe a question about this human annotator, inter-annotator thing. Have you tried to measure what's the human expert level of performance for these tasks? Like, I would imagine that not all the teachers are 100% right, so maybe it's not expected from an automatic system to achieve like 100%, but
yeah, actually we collected kind of small validation set where all the human experts review the same samples, but we haven't yet analyzed that how many errors. But by just looking at the data, it seems that they surprisingly often disagree with each other.
The sort of follow-up question: have you considered like separating the test data into like hard examples where the human annotators disagree a lot versus the easy samples where they agree?
Yes, exactly. That was what we were figuring out what to do with the last year of the project, is kind of analyze those. That would be interesting. And also to see that whether in those hard examples, whether also the machine is kind of disagreeing with the reviewers more than with the easy examples. So are the same things hard for computer as for human? We don't know it.
Any questions from people? I wonder if you can hear us.
Hey, can you hear us?
Yes.
Okay, we have a question for you.
I have to speak into this thing.
Well, I theoretically you just have to speak, yeah.
Yeah, sorry, the sound quality here is really awful. So you might have said something that I just didn't understand. Probably half of what you said. It's been really a challenge. Yeah, I had a question about. It seemed from some of your slides, at least, that it was almost like you were solving two problems at the same time, where you're rating quality of. Well, I mean, your tasks were kind of separated into two classes. You know, on one hand, you had the pronunciation and fluency. On the other hand, you had all the grammatical and lexical and whether they were answering the question correctly. Do you have that sense that these are two rather how would I say separable problems, and whether it would make sense to also evaluate them separately for the three I don't know how to call them, these grammatical or linguistic things that don't have to do with speech? It would almost seem to me like they could be evaluated just as well on writing, right? So if you gave the task in a written form, right, what you did last summer for vacation, right, would you be able to do the evaluation on the written answers in order? Do you know what I'm saying? I'm trying to separate out, are these problems really
very good question? Yeah, I was just thinking that they are not so easily separable as you might think of, because the kind of students, when they are learning a language, kind of everything evolves together. And also when we look at the human expert answers to these different categories or dimensions, we saw that they are very correlated. So if somebody liked the pronunciation, he probably also liked the kind of in general the speaker and the way. So it seems that for human evaluators it is surprisingly difficult to separate all these aspects. So in that way, I don't think they are easily separable. And what you said about the written answers, so it kind of first seems like the same task of kind of using a text produced by speech recognition or whether writing or evaluating these grammar and vocabulary. But maybe you can use the same methods for those. But it is kind of definitely more challenging to use the speech recognition output or even human transcripts, because it's kind of spontaneous speech is not very regular. So people can kind of have very long sentences or very short sentences. They can have breaks and they think about what to say next. And kind of many things are quite complicated there. But certainly for kind of pedagogical point of view, it would be interesting to have kind of also the written solutions by the students and kind of compare them together. Could be very, very useful.
Yeah, I mean, of course, you're attacking a much more challenging problem. This is much more ambitious what you're doing when you put them all together, and of course, they all evolve. All these skills evolve sort of in synchrony, they all evolve together in the learner. I was just thinking from the point of view of evaluation, whether you might be able to actually get much better results, for example, on the spoken qualities, if that was evaluated separately, where the student didn't have to, if we're interested in the student's fluency and pronunciation ability, would we be able to get perhaps a much more accurate evaluation if you asked him to read a pre-transcribed or a written piece of text?
Yes, exactly. Yes, you are right, and that's actually what we did also. So now I was talking only about these spontaneous speech tasks. But at the same time, we also collected read aloud tasks from the students, and certainly they are much better for evaluating the pronunciation and fluency just by following the reading, because then we know what the correct pronunciations are. But if the students are pronouncing some words that we don't even know what they are trying to say, and it's very hard to evaluate the pronunciation of those words.
Right, exactly. Okay, thanks.
Say also, Thomas was asking about this inter-rater agreement, but you could also question about this inter-transcriber agreement. So if you had several speakers transcribing the same speaker terms, would they give the same answer? And certainly the answer will be that no, they are not very good agreeing those either. So we have only kind of measured the agreement for native speakers, fluent spontaneous speech, and even there the agreement is not very great. And if you now take the language learners' speech, then that would certainly give quite high lower limit for the error rates.
Okay, I propose to close this session and we are free to continue the discussion offline. So yeah, thanks everyone for participating in this experiment, and we will definitely use the quality thing. So yeah, let's thank the speaker again.